Hi, thank you for attending my talk. I'm going to talk about how to train your robot, Introduction to Reinforcement Learning. My name is Craig Buhr. I'm a manager of the control design products at MathWorks. So the agenda for today will be how to train a robot. I'll spend about 35 minutes on this part of the presentation. We'll go over what is reinforcement learning, an overview of use in traditional controls approach, and then we'll work on applying reinforcement learning workflow for the same problem. And then we'll follow up with, finish up with a question and answer session of 10 minutes. So one of the common questions we get is how is reinforcement learning related to machine learning? And reinforcement learning is actually a subset of machine learning. Typically, when people think of machine learning, they think of unsupervised learning and supervised learning. For unsupervised learning, you have unlabeled data where you're trying to gather information about your data set, and often you do clustering in unsupervised learning. For supervised learning, you have labeled data, and often you try to do classification or regression, such as image classification or regression to predict what the next value will be given another set of input data. Reinforcement learning is a third type of machine learning where you're doing interaction data, and this is for control and decision-making processes. So this allows you to interact with the system, so you don't have label data, but you interact with the system to do your learning. And so the goal of reinforcement learning is to learn a behavior or accomplishing a task through trial and error, and that's where the interaction comes from. And typically, you might hear the term deep reinforcement learning, and that's typically you use deep models as function approximations for typically complex problems, and they require deep models. So there's a lot of applications that you can apply reinforcement learning to. As I said, it's good for decision and control application. So one of the most popular are video games. You see a lot of this with deep minds and a lot of stuff in the news with them doing very well solving computer games, playing computer games. But it's also advantageous using it in autonomous vehicles, controls of items, aircraft such as drones, and also robotics examples. And today we'll focus on a robotics example. So our goal today is to train a robot to walk a straight line. So how do we go about do that? So we need to determine a sequence of motor commands. What is the sequence of motor commands that we need to make the robot walk? So we actually have motor commands for each of the joint angles. We need to figure out what those commands should be and how they should be sequenced in order to make a robot walk. And this is what the goal of control is. So much like the robotic system, we have a system. We apply some actions to the system. The outcome becomes some sort of behavior in response to those actions. And the goal is to determine what actions generate the desired behavior that we're looking for. So the way the feed control works is we monitor the behavior with observations. This could be through sensors, through vision, encoders, etc. And from this information, we can get state observations. We can take those state observations, see how they deviate from what our target behavior is, and then using that error signal, we can apply a controller to determine what action should we take so that the behavior models our reference, our desired reference behavior. And this is what feedback control is. So this is just a quick introduction of feedback control to give a comparison to reinforcement or reinforcement learning. Excuse me. So if we looked at solving a walking robot problem with a traditional controls approach, we'd take our robot, we'd have our sensors, so we'd have our observations from our camera data, our sensors such as our gyros or our inertial measurement units, encoders, etc. From the camera data, we'd probably have a perception engineer do some feature extraction, so this is manually extracting features from the vision data. Then we'd take the sensors information and the features extracted from the camera data. We do some sensor fusion to extract additional state information about the pose, etc. of the robot. Using the state information, we'd design a control system which would determine the appropriate motor commands based upon those observations. And the control system would actually be quite complicated for a system like this. We'd have low-level motor commands, which are adjusting the motors to make the legs at particular angles. We'd also have leg and trunk trajectories. So, we have a gait that we need to follow for walking, the sequence of leg actions for walking. And then we probably have another loop which would handle balancing. So what happens if somebody pushed the robot, how does it recover from those types of disturbances? So as you can see, it's quite a complex problem from the perception piece all the way to the controls piece. So we can look at an alternative approach. So what would happen if we took all this stuff from feature extraction to control and we turned it into a black box controller? So we directly take our observations, determine what motor commands to provide to the system. The challenging part is, how do we go about designing this? And reinforcement learning is one way about designing this black box controller. So what is reinforcement learning? So one of the most popular books in reinforcement learning is by Sutton and Bartow. Here they define reinforcement learning as: reinforcement learning is learning what to do, how to map situations to actions so as to maximize some numerical reward signal. The learner is not told which actions to take, but instead must discover which actions yield the most reward by trying them. And this is where we talk about interaction data. It's learning based upon its actions given a reward signal. And probably the most easiest way to think about this is through an example with training a dog. So you have a person here training a dog. She yells fetch. The dog decides what it should try to do. The dog goes fetches the stick, so you give it a treat for a reward. And that treat reinforces that behavior that it did to receive that treat. So let's go into some of the reinforcement learning terminology that I'll be using throughout the presentation. So we have the agent. The agent and the environment are the two key pieces of the system. The environment contains everything except the logic for the control. So here we have the robot is part of the environment. We measure observations. It will go through a function called a policy. This determines what actions to take in terms of motors and torques. So in addition, in reinforcement learning, we use a reward signal that tells it how well it did. So you're getting reinforcement through rewards obtained from the environment. We'll go into more detail about this later. So how do we use this reward signal in terms of improving our policy? So if we look at the agent, the reinforcement, the agent consists of the policy, which is the function that maps the observations to actions. It also has the reinforcement learning algorithm. So the reinforcement learning algorithm takes in the rewards, the actions that it took for a given observation, and uses an optimization method to find the optimal policy that looks at trying to maximize a cumulative long-term reward. So the main thing about reinforcement learning is this algorithm, which is used to take this data and determine how to improve the policy function to improve its behavior. So what is the reinforcement learning workflow? So you can break it down into several steps. So first, we need an environment to interact with. We need a reward signal, which tells us how well we're doing in accomplishing the task or the behavior that we're trying to achieve. We have a policy/agent, which determines what actions to take and how do we improve the policy. We go about training. The training is actually the process of collecting the data of interacting with the environment to improve the policy. And then once you've trained an agent, you often want to deploy it. So you can deploy it to an embedded system. And so we'll go through each of these steps in the workflow. So let's first look at the environment. So environment, like I said, is everything outside the agent. So the agent is the brains of the system. It sends out the actions, and from the environment, it receives the rewards and observations. So for this robotics problem, we have a biped robot. We'll have several sensor measurements coming in, which are the angles of the joints, the acceleration of the angles of the joints, the inertia moments, etc., of the torso. So kind of the measurements of the pose of the robot. In return, the agent will send out action, which are the torques to each of the motors. So there's 3 motors in each of the legs for the ankle, knee, and hip joint, and that's for the left and right leg. So there's 6 actions going out altogether. So when we do reinforcement learning, you have two choices. You know, do you use a real environment to do your learning on, or would you want to use a simulated environment? So there's some pros and cons for each of these. So one of the benefits of using the real environment is that you have accuracy. You're actually learning on the system that you're trying to control. The downside is risk. So as you learn, you're going to do a lot of actions. You're probably the robot's going to fall over quite a bit. It's very data intensive, sampling intensive. So you need a lot of data, so you could actually do some wear and tear on your motor parts as well, your robot parts. However, if you look at a simulated environment, you actually improve things with training speed. Oftentimes you can run simulations faster than you can run stuff in real time. In addition, because it's a virtual simulation, you can actually run 10 simulations simultaneously, and you don't actually have to have 10 robots. It also provides you flexibility in simulation conditions. It allows you to simulate conditions which you may not want to put the real robot in such a situation. And that includes safety. You know, working in a simulated environment, you don't have to worry about the robot hitting something or coming in contact with another person. So the simulation environment provides safety as well. The downside is model inaccuracy. So because you're working on a simulated environment, it's an approximation of your real system. So those mismatches can have issues when you actually go to deploy the system on the real robot. But there's ways to mitigate that through system identification, parameter estimation techniques to improve your simulated model to represent the real world dynamics. So in our case, we're going to look at the simulated environment for our session. All right, so there's lots of ways to model systems. Here we're using Simulink. It's a modeling package by MathWorks, which does dynamic system modeling. Here we have a physical model of the robot. We're using it to model the dynamics and contact forces using the physical modeling package inside of Simulink called SimScape. If we go inside of the robot block here, the dynamics inside of here, what we'll see is if we open up this walking robot block, we actually see the different pieces. So we have the robot legs, left and right. We have the hip and torso joints. We have the contacts with the world and ground and the main torso. If we go inside of a particular robot leg, it actually has each of the limbs connected together. So it's a nice physical modeling package to create these types of systems. And this final block shows all the sensor measurements that we're extracting from the model. So now that we have our model of our robots, the next thing we want to look at is the reward signal. So as I mentioned, the reward is kind of the feedback that the agent gets to determine whether or not it's doing well. So the reward function is a scalar number that represents the immediate goodness of an action that an agent takes at a particular state. So one way when you go about defining the reward is often it's good to use your domain knowledge in defining the reward for a system. So in this case, we're trying to coerce a robot to walk. So what is a good reward signal that may help the robot learn how to walk? You know, how do we give it feedback in terms of how well it's doing? So in this case, we have a reward made up of several components, and I'll go into more detail of this later in the presentation. But for right now, we'll just go over what the reward signal that we use in training the robot. So our goal was to make the robot walk. So we added forward velocity as a requirement. We also wanted to follow a straight line. So we added a negative penalty for deviating from the center line, which is the -3y squared. We also want to keep the trunk height at initial height. So this is kind of, we don't want the robot to fall over or lean too far forward. We also have a reward for how long it walks. So how long each time step that it takes that it doesn't fall over, we give an additional reward. And then the final reward that we have here in the reward, or final term in the reward function, is to minimize actuation effort. So we want it to be efficient walking. So we want to minimize the energy that we send to each of the joints of the robot. So in the Simulink model, we can define our reward signal in this block here. If we go inside of that block, basically we create a block diagram representing this equation for the reward function. And this could also be done through a function block as well, where you'd write actual code for this equation. All right, so we've done 2 steps already. We defined the environment, the reward. The next is the policy and the agent. So as we mentioned, the agent is what does the learning and receives the information from the environment. So I showed this block diagram earlier. The policy is what maps the observations to actions, and the reinforcement learning algorithm is the optimization that's used to find the optimal policy. So there's a lot of different types of method. There's value method, policy gradient methods, and actor-critic methods. In this example, we're going to talk about an actor-critic method, and I'll kind of give just a brief overview of how this works. So in the actor-critic method, we actually have 2 neural networks. Typically, there's 2 neural networks, and they're simultaneously tuned during training. The actor tries to learn the best action at each state, and the critic tries to estimate the value of each state that an action that the actor takes, and it's kind of a critique or a guide to give feedback to the actor of how to improve itself. And when I mention that it estimates the value is denoted as the total reward the agent expects from that state onward following that policy. So this gives an idea of how much reward does it think it will get overall if it takes a particular action. So let's look at what the actor-critic training cycle looks like. So we have the actor-critic set up here. So as I mentioned, the actor is responsible for choosing the action based upon the state observations. The critic is responsible for predicting how good a value that will come out of that action. Once it takes that action, it'll actually compare the reward with its value, and it does this using a Bellman equation. Don't worry too much about the equation, but basically it gets an error from what it predicted the long-term value would be versus its next best estimate, new best estimate of the value. And using that error, we can use like a stochastic gradient descent approach to update the critic. Once we have the critic update, and the critic becomes improves its performance at predicting the value function, we then use the critic to update the actor. So we both update both these models, and the critic is used to improve the actor's performance. So you think of it, just in the terms that it is actor and critic. If you have a critic criticizing a film, they give a feedback on how well the actor did, and the actor then can improve its performance in the next show. So this kind of gives the overview, a general overview of how actor-critic training cycle works. So the next step we want to do is create the training agent for a system that we'll actually use for training. We're using a method for this example called deep deterministic policy gradient. The key parts here is that we need to create a critic network, we need to create a policy network, and we also need to create the agent and the hyperparameters associated with that. So let's go through those steps for this problem. All right, so if you create a critic network, so here we're using a tool inside of the deep learning toolbox called the Deep Network Designer. The nice part about this is it's a graphical environment where you can actually take blocks, neural network blocks from the left layers and drag them to the right. So here we created a neural network with 2 inputs, one for the state observations and one for the action. It goes through some fully connected layers followed by some ReLU layers. They join paths and go through another activation layer. So that's our critic network that we defined for this system. We also define an actor network. Here we have our state observations to actions. So we have our observations coming in. We go through a few fully connected layers with ReLU activation layers. And then our final layer here is a TANH layer. And this is because we have bounds on our actuation for our motor torques. And so those are encoded into this TANH layer. All right, great. So this is a nice, easy way to create the networks for our system. Once we have the networks, we can use the reinforcement learning toolbox to represent the agent. Here we set up our hyperparameters, such as what optimization methods we want to use, what learning rates. We create the critic and actor, and then we pass that into the reinforcement learning deep deterministic policy gradient agent. So this constructs this last line of the code constructs the agent that we're going to use for our problem. So now that we have the object created for the agent, we can actually put that in our Simulink model. So the agent is represented by this block in the Simulink model, and we can pass that agent to that block. So now we're all set with setting up the problem. So the next step we want to do is training. So now we want to train the agent. So when we're training a deep reinforcement learning agent, I mentioned that it's very sample and efficient. It takes a lot of data, a lot of trials and error to learn the system. So to accelerate training, one of the big benefits of working in a simulated environment is that you can run simulations in parallel, using multi-core computers, clusters, or the cloud. So if we look at how this works, we have the client. It fires up a bunch of simulation jobs to each of the workers. The workers run a particular policy collecting data. Those workers send the data back to the agent, the main client. This is where the learning happens. The agent then updates its parameters and then sends those parameters back to the workers to run some more experiments with its updated policy. So this improves the time it takes, reduces the time it takes to do learning. In addition, you can actually leverage other resources too. You can actually set the neural networks to either compute their policies or compute their data using GPUs or CPUs. For really deep networks, GPUs will provide a significant advantage. So if we look at the code required to do training, we set up our training set. We set the number of maximum episodes we want. We set up the max number of steps per episode. We set up our criteria for stopping. So once we reach average reward of 100, we'll stop training. Listed here, we are going to use parallel training. And then once we set up these parameters, we just call train with the agent environment and the options. We fire that up. So I have a video here. It starts out at normal time, but then it speeds up a little bit faster than normal time. So here, the blue line is the reward at each episode. The red line is the average reward. So the goal is hopefully this goes up and to the right until the red line reaches 100. Some of the things that you want to do while training is something called domain randomization. So you want to start at different initial conditions, vary some of the parameters in your system. This improves robustness of your resulting policy, which will make it more likely to work when you deploy it to hardware. The other main thing that you need to look at is exploration. The policy needs to explore to learn. So exploration is one of the parameters that you set, how much exploration you want to do before you start taking the best policy. So we're actually able to train. We reached our goal of 100, and so we're ready to see how well the policy did. So we click play in our Simulink model, and we see the robot walking, doing well. We see the data that's on the right. We have the cumulative reward in the middle plot there, and we see the robot's doing a good job of walking and following the lines. So we're able to walk through the whole workflow here, from defining reinforcement learning, setting up the problem, and tuning the system. But I would want to go to one step and revisit the use of the reward function. So, this went nice and smoothly on one process, but typically there's a lot of iteration when you do reinforcement learning. In particular, there's one area called reward shaping, which really helps improve the learning outcomes. And I'll kind of go through that process now. So the reward function design really matters. So, if we just looked at this and we said, I want my robot to walk forward, let's just use forward velocity as its reward, which makes sense. We want the robot to move forward, so let's use forward velocity as the reward. So if we only use forward velocity as the reward, this is the behavior that emerged from the reinforcement learning training. Basically, it developed a little bit of energy, leaned itself forward. Based on gravity, you got this initial high velocity coming out of X, and it got stuck in this local minimum. It may be able to get out of this local minimum with additional exploration, but this is one of the challenges with reward functions. So the next thing we did, we said, well, let's add additional reward. So since it's fallen over, let's give it a reward for each time it stays up. And since we know we want its torso height to stay at a certain, relative nominal height, let's penalize it if it doesn't maintain that nominal height. So if we use this reward function and start training, we see it does walking behavior emerges, but it's very, not maybe the typical walking. It kind of looks like a zombie, walking, dragging its leg. So while it's actually improved its, behavior of walking, it's still not quite what we want. So the next thing we did is let's add a penalty to energy for actuation. So this is trying to make the robot motion more efficient by using less energy in the robot walking in the reward function. So if we do this, there's the term. If we do this, we see we get good walking behavior. However, it's not staying across the line. And so you notice that it's walking more like a human, which makes sense because as we've evolved, our walking gaits have become efficient. However, we see we're not really tracking the center line like we wanted to. So the next step, what we did is we add a reward function, which is penalizing deviation from the center line. So once we do that, we see the robot walks the line. If it starts deviating from the line, it starts walking back. So we're really seeing how using your domain knowledge, you can actually improve your learning outcomes through reward shaping. All right, so we've done a bunch of training. We've kind of seen what are some of the iterations that you need to do during training. The next step is deployment. So the next step is we've done our learning offline. We have our policy. We have our target hardware with some embedded processor, and we want to take that policy and push it to an embedded processor. So we can, with the MathWorks tools, we can automatically generate C or C++ or CUDA code to run the policy on embedded systems. Basically, this works as follows. You take the policy, use our code generation products. MATLAB Coder allows you to push it to an ARM compute library or Intel MKL DNN library, or the GPU coder allows you to generate CUDA code to run on an NVIDIA processor. I don't actually have a robot to deploy this on to show that demonstration, but this is the process that you would go through to then generate code for your final system. And so the key takeaway of the talks are, we kind of went through the process of reinforcement learning, got an idea of how it works and what it takes to solve complicated control and decision processes. It's gaining a lot of traction in the industry with many of our customers, so it's actually looks like it's going to be a good technology. There's a lot of things that you can do. Reward shaping is one that you can use to improve learning outcomes. Using your domain knowledge, embedding your domain knowledge in the problem really improves the sample efficiency and the outcomes that you achieve using reinforcement learning. And then finally, in this particular case, we use MATLAB and Simulink to demonstrate the workflow of reinforcement learning, and we work through a complete workflow for leveraging deep reinforcement learning. Thank you for listening to my presentation, and let's open it up for the last 10 minutes for some Q&A. Thank you.